Perfect. So I'm Logan Ward. I'm a computational scientist at Argonne, and today I'll be talking to you about a project that's been going on at Argonne for a couple years as part of the exascale computing project. Namely, what we'll be speaking about is Colmena, an application that we're designing to allow people to steer workflows of simulations using AI. And the big motivation, at least in terms of this being part of the exascale computing project, is that increases in computational power means that the amount of data being produced by an ensemble simulation is going to grow rapidly, and it's going to come much more quickly. And so what this means practically is the very common pattern of a human identifying a set of simulations that they want to run, dispatching them to the supercomputer, waiting for them to complete, and then making their decisions about what to run next is going to become very inefficient. There just won't be able, humans aren't going to be able to come up with lists of simulations at an appropriate rate to keep up with new supercomputers. So our goal here is to explore the idea of how we can offload that task of deciding which experiments will be of the most value to the supercomputer itself, namely by creating some kind of AI agent that can steer the set of simulations. So when approaching this problem, we identified two kind of main challenges that make creating these kind of self-steering HPC difficult. One is the fact that these AI agents themselves are computational, have computational costs that are not trivial. And considering the growth of the computational costs of common deep learning tools, it's going to be increasingly tasks that you can't just run on your login node or the laptop that you use to submit those HPC. They needed dedicated computing themselves. And additionally, creating these apps is a juggling process of making sure the right AI model is attached to the most recent training data, and that all of these are hooked up to the right simulation queue. So considering these two main issues, we've developed a program we're calling Colmena that facilitates building these kind of applications that allow you to create steering applications that will say dispatch tasks which are determine what simulation to run next onto a set of nodes dedicated for those AI tasks, and being able to deploy computation out to the compute nodes as appropriate for the simulation aspects. So what we're going to go through today are some of the design goals and how we've approached them so far by using surprisingly Parsl profusely throughout this application. So Colmena itself is indeed built heavily using Parsl. The idea is we provide a client application a simple interface for being able to deploy functions across HPC. So what this provides, in short, is a queue-based model for being able to receive data from a supercomputing system and be able to send out new task requests of predefined functions out to those workers. Now, what actually happens under the hood is these tasks are communicated using a JSON markup language over Redis queues to a method server, or at least one method server, depending on the scale of your computing needs. And these are translated into Parsl tasks, which are dispatched to whatever computational resources you have available. Naturally, we're targeting these towards high performance computing systems, but we've also used Colmena already in a way that combines HPC for simulation, with more local GPU resources to engage the AI tasks on hardware that better support the scale of the challenges required. So to give an example of the kind of tasks or the kind of tools you can build using Colmena, we can explore a few different kinds of parallel optimizers. And these slides will give you a link to our GitHub page that show all of the code. But for the interest of time, we're going to skip looking at any Python today. So with this idea of distributed optimization, there are a few different patterns that have already emerged in the literature. There's a very common scatter-gather approach where you send out a block of tasks, block until they complete, and then use that new data to identify the next batch to perform. And you'll note if your tasks vary significantly in runtime, this can lead to some difficulties in maintaining a system with useful work. You can also build a streaming optimizer that, as soon as a task completes, engages the AI component to produce another task. And if your rate of tasks exceed the rate that you can produce them, you can also see some utilization difficulties with this algorithm as well. The kind of application, which was the motivating case for building Colmena, eliminates these two latency problems we observe in a batch or a streaming optimizer, and ends up creating an application that looks like a very agent-based software. What we're using for molecular design to create this interleaved task queue is an approach that divides work into multiple different independent agents. We have simulation workers that simply acquire a task from a queue, run that simulation, and then store the result in a database. And we can run many of these concurrently. There's also a task management system that maintains an iterative process of continually refreshing that work queue. And it does this by updating the surrogate models we use to predict the outcome of simulations, using them to generate a new set of tasks, and then finally, using active learning techniques such as Bayesian optimization to ensure that these simulation workers are picking from the best tasks first. And we can use this to maintain fairly high utilization on an HPC system. As an example, this is showing results from a debugging run of 8 nodes on Theta, where we're able to have 112 simulation workers that need to be kept busy and able to dedicate a single node to performing the AI tasks. And you note that we can create a system that provides an ample rate of task generation to keep 90% of our system busy at any given time. And Colmena is also built to further studying these scaling issues. If we take a look at these charts, which are derived from those JSON messages that track the task provenance as it moves through the software system, we can take a look at where the breakdown in our scaling issue is so that Colmena itself can be used as a research tool for exploring routes for distributed optimization. So that's effectively all I wanted to talk about today. In short, Colmena is a package built on top of Parsl that enables you to create intelligent agents for picking which simulations to run. And it's a code that's already up on GitHub with an associated read the docs. If this happens to be a tool that's interesting to you, I encourage you to take a look at our GitHub or reach out to me, and we can figure out if there's some capability here that might solve problems that you're seeing. At this point, I'd like to thank, of course, my funding and the rich team at both Argonne, Brookhaven, and the University of Chicago that's helping to build this tool. And I'd be happy to answer any questions that you have. Thank you all.
Wonderful. Thank you, Logan. I think we've got time for one quick question, and then JB, you're up next. So a quick question from the audience. It's unfair for me to ask a question here because I know Colmena inside and out. Yadu, do you have a question? Be even more unfair for you to ask it, but I encourage you to do so.
Yeah, I had a question, but sort of about like where would you see some of these components getting offloaded? Do you think GPUs might help in offloading some of the AI components?
Absolutely. Both AI components for, say, or like GPUs for retraining the models, I envision being very useful, as well as dedicated systems like the Cerberus machine at Argonne that really shortens the time necessary to update a machine learning model by really dedicating hardware design to that task. where one could imagine that Parsl's multi-site ability lets us have a single software app that uses those accelerators for the tasks for which they're intended and use general purpose HPC for everything else.